I'd like to talk a bit about Math 249 Combinatorics courses. I'd like to talk about an advanced class called Math 249. So we have an awful lot of good students amongst our 1,500 or so first-year students. Maybe 80 or 100 of them take advanced classes in algebra and calculus, and 20 of them survive with all their zeal to second year. And we teach them a beginning class in combinatorics. And I give them a session about counting, and I love counting, and then we do some stuff that I can't remember. Oh, I got to focus too. Speak slowly and clearly and face the audience. I've been taking some tutelage with Cynthia because I haven't taught for 3 or 4 years. And it's not that easy. So we have these students, they think they're really smart, and they are. But they don't know quite as much as they think, of course. So I like to start them with something elementary in counting. And I like to make sure that I pass from something trivial to something they have to think about to something they actually have assigned in a minimum time. And I guess I have to do an untroy. So I won't ask for your participation. I'm not interested in what you think or have to say. And I won't make jokes about grade 11 or grade 7. My 13-year-old tells me it's when she got that stuff in grade 7. She already knew it, Dad. So, but we won't go there. Cynthia says she thinks it should be bigger. Can we get rid of this crap here, please? Those guys in the School of Computer Science, they try to sabotage everything. So you all know the most elementary counting problem we can have, which is to determine the number of k subsets of an n set, which is to say, I take your favorite set of n distinct elements. Mine happens to be the integers from 1 to n. I don't know where the numbers stop and the letters begin with 1 to n. So I'm going to take 1, 2, 3, 4, 5. It's my favorite 5 set. And I'd like to find out how many subsets there are of size 3 chosen from that. I hate commas, so I'm just going to tell you which elements are in the subsets. Haven't done this for a while. I didn't prepare that. I suck at this a little bit. So you have this bucket of 1, 2, 3, 4, 5, and you grab 3 different guys and you fire them down. You do it in all possible ways and perhaps give it a coherent order. And after you've found 10 of these 3 subsets, there are no more. So the number of 3 subsets of a 5 set is 10. We define that to be this symbol, which has 2 parameters, n and k. I really like to read mathematics to my family. Whenever my 16-year-old tells me how I should be driving, as she did on the 401 when I was going 140 kilometers, and she could read it over my shoulder on the weekend, I tell her about mathematics. And of course, it's hard to tell her left parenthesis and right parenthesis and n over k centrally spaced, so we have our own language, n choose k. Of course, it is a mnemonic, a memory aid, because it tells us how many ways we will choose k elements from a set of size n. What's the value of n choose k? You all know, clever as you are, that the value can be determined as a ratio of factorials. And as you know, that sign that often says that you're excited about something, and excited is actually read n factorial. And it is the product of all the numbers from 1 to n, if n is a positive integer, and as a pathology or not. 0 factorial is defined to be 1. Use that as an empty product convention if you like. Check the number of 3 subsets of a 5 set. I'm going to calculate it in this way. I love to cancel, even when they're ones. It's the power of being a professor. 4 over 2 is usually 2. Oh, and 5 times 2 is 10. Hooray! So you know that n choose k is defined to be this term, and it has this value. Now I'd like to slide this board, but I'm old and weak. Beautiful. So when you read your elementary textbooks about counting and n choose k, it's often phrased in a geometric setting. The number of up and right paths So you imagine yourself that you're starting at the origin, and you have an integer unit, 1, to go up or right at each stage. And you want to arrive at the non-negative integer pair m and n. And you view this in time, you start, you make a decision. I'm going to go right and up. And maybe right again, and maybe right again, and then up. How many paths are there from 0, 0 to mn? The answer is m plus n choose n, as you all know. One thing we're going to find very powerful when we talk about combinatorics is bijections, or one-to-one correspondence. So I'd like to make sure that I understand that this is exactly a pictorial version of something that lives over here as my favorite k subsets of an n set. Here's a good way to do it. I want to go from 0, 0 to 3, 2. Every time I choose a u, I increase the y coordinate by 1. I never go back. Every time I choose an r, I increase the x coordinate by 1. I'm going to have 3 plus 2 or 5 increases to get from beginning to end. And then I'm going to have to stop there. 3 of them will be right, and 2 will be up. I'm going to be, if I walk along this path, I'm going to read out in positions 1, 2, and 3 plus 2. I'm going to read out first step is a right. Second step is an up. Right, right, up. So if I want to take the picture out of this, I can linearize it and simply give you a list. A list of u's and r's from beginning to end. Of course, if I index these positions from beginning to end, the r's occur in a triple, a 3 subset chosen from the 5 set. And thank you. I don't want your participation, but sometimes I need it. Oh, shoot. I know why Willard served as a chair for so long. 1 and 3 and 4. Indeed. There's a one-to-one correspondence between elements of this bucket of the 3 subsets of a 5 set and the 3 subsets of a 5 set, the paths that are 3 rights and 2 u's. Now I would like to remove this question mark. The geometry is pretty hokey there. So I'd like to talk about the ballot problem. Imagine, if you will, that a U is a vote for Ms. Underwood, and an R is a vote for Mr. Robertson. And you have an election in which you have N votes cast for each, and you ask, well, they have the same number of ballots, but in how many of these, in how many ways in which the votes were cast did one never trail the other? You never want more Robertsons and Underwoods. Geometrically, how many seconds do I have, Cynthia?
About 90 seconds.
So I want to go from 0, 0 to NN, and I never want to stray into this region below. One classical way of counting it is to take all those bloody paths. 2n, choose n of them. And then subtract off the numbers that do go below. B for below or bad boys, whatever you like. Professors like to be megalomaniacs, or I do. Professors as deans and chairs, perhaps, Ross. Suppose I want to count the bad boys. And I set myself up there about a half a unit below the line y equal x. And I ask you to take your path. You've got 2n, choose n of them, and just put the steps in order. So you put an up, and you wander around, you touch this line, you wander around, you touch this line. And the moment you stray across that line, my laser beam coming out that line has a hit. And I say, oh, that's a bad path. It's a bad boy coming. If I never, ever get a hit, your path is fine. If I ever get a hit, then I hit it for the first time and I say, throw it away, start again. Let's say I want to count them. I want to count the bad boys. I know that they always look like some portion right here. It might be null. I might immediately hop right. I will pass into the region below y equal x for a first time with a horizontal step. I will record that all in the LaTeX notes on the website. And then I wander around until I get back there. Suppose that I, with all the power that I have, deem that I'm going to take this and reflect it. About the line y equal x minus 1. So y equals x becomes y equals x minus 2. This point 0, 0 becomes 1 minus 1. Claim. If I do my same megalomaniac shtick on the new path, having replaced this initial portion by that red guy, I'm going to see this as the first guy in the passage from y equals x minus 2 to y equals x minus 1. I'm going to see it coming up. Claim every path from 1 minus 1 on the line y equal x minus 2 to nn on the line y equal x minus 0. We'll pass through the line y equal x minus 1. We'll record that in the notes. And I'm going to trap it the first time in the reflected image. So every damn path from 1 minus 1 to nn will pass through here. I can reconstruct the bad boy whence it arose. And so there's a one-to-one correspondence between every path, which are easy to count. After all, there's n minus 1 here and n plus 1, and 2n, choose n minus 1. And the bad boys. Claim. And I'll stop now, Cynthia. The ballot number is exactly this difference. Bye-bye.